So let's talk statistical issues surrounding the monitoring of bees. Monitoring of bees is going to be defined as an unbiased measure of bee population change over time. So some of the issues around bee sampling are that bees have really high variances. So that lowers your ability to detect trend because the variability in populations is huge, particularly compared to vertebrates. So looking at other monitoring programs for birds and amphibians is going to be not as good an example as you might expect because the variability in bee populations, as you'll see, is so much higher. So we also have a lot of biases of different kinds that take into consideration when crafting a new monitoring program, such as observer techniques, locations, to always keep in mind as we go. And it turns out that rare species and uncommon species and getting a good measure of change for those are going to be the drivers in your monitoring sample sizes, whatever the program is. So these are a set of factors. We're not going to cover them all, but these need to be addressed in any monitoring program. I'm just going to list them. Target species involved, statistical frame, the sampling strategies, the survey protocols, the time periods for calculations of trends, what are the subregions for which you want to talk about trend within the larger overall context, the time periods for the calculations, what trends over how many years do you want to talk about, the degree and type of trend, alpha and power levels, we're really not going to talk about those, and sampling locations, the numerics on that, and so that's a power analysis of some kind. We won't address those, we don't have time, but that is what you want to see when you're setting up your monitoring programs, that you have thought about and have addressed those, and so you don't get bitten by them later by not having addressed them. So practically speaking, you need to be sampling in any kind of monitoring program that's going to give you quality data. You need to be sampling a lot of bees. So there has to be a lot of bees, there has to be a lot of samples because you have to cut through all that variation. And the more subregions you want to talk about, like you may have a global, not global, let's say a United States level program, but if you want to talk about the states within there, you have to greatly increase your samples in order to talk about those subregions too. So there's consequences for how small an area you want to discuss population trends. You're really resetting a whole monitoring program for those subregions. So trends over short periods of time, like estimating 2 or 3 year population trends, are going to require many more samples than being able to look at that over longer periods. And so realistically, you're going to be looking at change over long periods of time. So what makes a good monitoring program? Clearly defined questions at the beginning. What are your goals? It's repeatable, low variance, as low as you can get realistically. Costs are low, and then you want to have a accurate measure of change in populations for most of the pollinator community. So you need to bring in as many of the species you can, which means multiple techniques in most cases. 3 factors are affecting your sample size: variability of your sample, how you define precision, and what you mean by trend or change. So the only thing that really matters that you have to get from somewhere is that variability estimation. So we're going to talk about variability as the standard deviation divided by the mean, because they're correlated. So this is what's called the CV. It just standardizes the variance term. So bottom line, high CV, that's bad. You don't want a high CV because that means that you have a lot of noise to cut through before you can detect a trend that's going on within a population. It would be great if we had time to define what we meant by precision and all those kinds of things that have to do with that. We really don't have time for that, so I'm just going to skip it. We can talk about it in breakout groups. You also have to define what you mean by trend, and that means you have to give a time period, and then also how small or large a trend you want to be able to detect within that time period. So do you want to detect a 1% change in population, a 10%, whatever? You have to define that, and that's going to have impacts on the number of samples. So another bottom line, being able to detect a small change is going to cost you an awful lot in sample sizes, meaning you have to put in a lot more than being able to detect just some large kind of change. So when I work with monitoring programs, this is often ends up to be my favorite ones for most kinds of programs, where I want to have an ability for whatever the species is or species group to detect a 50% decline. It makes sense for most people over a set period of time, and that I set these precision values, which we're not going to talk about. Time frame is actually 10 and 25-year scenarios, nothing less, because most people just, once you do the numbers, you really can't afford to talk about anything less than 10. So in that regard, as you go along, you have this steep drop-off in the number of sample size requirements that occur greater than 10 years. And at 25, it just stabilizes. You really need only a handful. But the problem is that if you set up a monitoring program, say for North America, and you put in the small number, it can be down to 20 or 30 sites to be able to realistically detect trends. The problem is that most species will not occur at those 13 sites. So you have to take into account that sampling locations do not get every species every time. You're not going to, with 13 sites, detect 13 of the southwestern desert species. And even if you have locations within the southwestern desert species, doesn't mean that you have gotten them then. So that is a multiplication factor that's huge, and again is not considered sometimes in these power analysis kinds of approaches, because the sample sizes may look small, but the number of sites you need to pick up the species, the geographic scope, becomes large. So another thing to consider is that there is a very big positive for instead of using counts of individuals, counts of locations. You're dealing with a proportion rather than a much greater fluctuating number, which is total number of individuals. In lots of scenarios, you can use both by gearing it towards estimating number of locations that a species has huge advantages and kicks us towards atlas types of approaches, I think. So when we look at variances, and we have done this, we've gone through the literature and we've gotten different people's long-term data sets, and we look at the variability of different kinds of techniques. You would think there's big differences. There's not. They basically all have the same kind of variance structure, counts by visual counts, by cup traps, by bowl traps. All those kinds of things have basically the same nasty, large variance structure. And so the lessons from that, and the lessons from doing different kinds of combinations, is that you can pool some of these kinds of things. So if we pull the data across species, surprisingly, the variance structure goes way down. So when you want to estimate species richness or total number of individuals, so not a lot of information, but if you want to be able to talk about change in all bees, you do that well. Almost every site has bees, and it turns out that these monitoring programs have a great ability to talk about how are bees as a class doing, but not by species, because the variance is huge for species. When you pull across time, ditto, you also get a big advantage of doing that. When you pool sites, like if you say, well, we're going to combine several sites and that will be advantageous, turns out it's not. Here's just one example, the only data slide. And if you look here, this is data from Czechoslovakia. Lovely, lovely data set. Long term, we had to actually trend the data before we could look at the variances. And you'll see by the different color bars, not a lot of height differences among different combinations of sites. So therefore, we don't really gain anything by pooling sites in this case and in all the other cases that we've looked at. If we look at all individuals, what you want to be is you want to be right around 50%, a CV of 50%. These are averages, and you can see like most individuals are way off the charts in terms of their variability. When we just choose species that occur at least once a year, which a surprising number occur at low numbers, all of a sudden our CVs the average is a lot lower. So common species, when we do greater than 5, we also have a little more advantage. And we look at the top 5 most abundant species, again, we have about the same number. We're in a range in which we can talk about individual species trends for this much smaller group, whereas most individuals are just off the charts, can't can't talk about because they vary so much from year to year in this particular one study. When we combine things and we just ask about how the variation is in the total number of individuals, it's really low. So this really allows us to talk in very precise terms about changes in total individuals. Ditto on number of species, species richness, really, really low here. And that occurs, this pattern is across the board in all monitoring sites and programs. Okay, so wrapping it up. So where to sample? This is another big issue. You might say, well, we want to sample the United States, but the problem is that if you do that randomly, a lot of your sites occur in low species richness sites that you may really not be as interested. And there's a penalty for doing that. So a lot of your uncommon rare species that you may be interested in are not going to show up. So you have to bump up your samples to do everything along those lines. So you could stratify, or you could just say sample just protected areas. If you're into agriculture, you might just do agricultural areas, just fruit crops of different kinds, just urban. You don't necessarily have to randomly choose your sites. You can choose places that up your chances or are of more conservation concern. So when you also think about counting, you have the problem that most people can't identify bees well. So, and if you look at starting gigantic amounts, gathering so much data, what's going to happen is we don't really have that identification capacity right now. So rather than get concerned about that and not do anything, think about archiving most of your initial efforts. So these efforts, and we can talk about that later, we don't have time. So you collect it, you archive it, and then you can do some minimalistic kinds of things. For example, simple counts of numbers of bees and the wasps and flies that get caught in these kinds of things are going to give you that trend, that very nice trend in species richness. You have middle grounds where you add on top of that maybe splitting out certain genera, like pulling all the bumblebees and working those to species, but leaving all the lazy glossums, which most people flip out about, and then making decisions about whether you're including the sex of the specimen or not, because those are different kinds of trends, give you different portraits into what's going on. So when you're archiving, think about not pinning up everything as your archival factor, but either leaving things in liquid or better probably processing and drying and keeping things in petri dishes that have no bug issues. So the key here is that if you don't do that because you're afraid you don't have the resources or time or expertise to identify bees, you can't go back and resample. So we can't go back to the 1800s and resample those any locations, right? We have no idea because nothing was collected. If you don't collect anything now, then you can't go back later and redo that. So better to collect it and archive it than not to collect it at all. This is the last slide. So these are my recommendations, and it's completely open to interpretation and changes, but this is kind of what my thinking would be. You would have an atlas block framework for whatever that means, and that could be counties and sub-counties within the United States are your blocking factor. So those would be the atlas units, or it could be the many other kinds. You divide it by the national grid or something. Primary sampling frame would be protected areas, because that's where most of the species of conservation concern are going to end up, and those are the areas that we have an ability to manipulate and think about and make changes to, and the rest is sort of going to be a trajectory that we have little control over. The primary standardizing techniques is going to be a trapping one, because a lot of the others, like visual observations and netting, are hugely biased and very problematic in terms of observer skill, particularly observer skill over time. The next sampling period, people may be a whole lot better. Now you're looking at change in bees and change in observers, and you can't disentangle those two. So sub-surveys then would be added into this, or could be added into this, depending on what people want to do for different kinds of things like urban areas. They could also sample, have target specific rare bees on rare plant communities and sand habitats, for example, which would drop out in a randomized scheme even in conservation areas. You would have teams of people who were expert at netting that would help add in unusual and uncommon species. Maybe, maybe not so repeatable, but at least you would get records for uncommon things and get some understanding of locations. And then random observations would be kept separately, but would be included, so you could add in iNaturalist kinds of information, but you want them to be divorced to some extent from the samples that have the standardized technique. Because over time, you're going to be, most of your information is going to be about changes in your standardized technique capture rates in order to talk about how things are doing. Okay, that's a wrap. Let's stop that.